So this is the beginning of section 11.9, and it's representations of functions as power series. So in this section, what we do is we take certain functions and write them as sum of power series. The question is why, and the strategy is useful when you're integrating functions, when you don't see the antiderivatives easily, or they're called elementary. They don't have elementary antiderivatives, for solving differential equations and for approximating functions by polynomials. So we're going to look at what we did in 11.8. So let's start off with 1 over 1 minus x. And we know that when we look at this, we have 1 plus x squared plus x to the third, and so forth. And we call this the sum from n equals 0 to infinity of x to the n, where the absolute value of x is less than 1. We talked about, in the last section, we talked about the fact that this was geometric. And so if we have a equals 1 and r equals x, and we can talk about convergence and divergence. But what we're looking at in this section is we're looking at the function f of x equals 1 over 1 minus x. Now this is leading us further, so you have to pick this up, but we're going to be doing more with it. But since we have this, the function really is the continuous function, so it can be written as the sum from n equals 0 to infinity of x to the n, where the absolute value of x is less than 1. So what we're looking at in this section is the fact that our functions can be written as power series. So the important thing to note is you can get an output or a y value, and this output really only is valid if your input are the n values that make the series converge. So we're going to look at this more carefully. So here you can see the red graph represents the f of x, which is 1 over 1 minus x. And then you can see that as our partial sums get better, we can see it gets closer to the graph approximating the function. So let's look at an example. It says express 1 over 1 plus x squared as the sum of the power series and find the interval of convergence. So let's make a note that, and remember that 1 over 1 minus x is our basic power series. So we want it to look similar to that. So think about what that means is we could write this as 1 over 1 minus negative x squared. You understand that those are equivalent values, so we're good there. And then that really means that we have 1 over 1 minus negative x squared. Let me put that squared inside. So this right here, this parentheses is in place of the x. So it follows the format of x, but the parentheses is going to be in the summation. So we have the sum from n equals 0 to infinity. So that means in place of the x, here we have negative x squared to the n power. Now, we can look at this and say this is the series of, let's split it and say negative 1 to the n power and x squared to the n power. So this means we have the series from n equals 0 to infinity. Negative 1 to the n, we could call this x to the 2n. So now let's look at a few terms. This would be negative 1 to the 0 power is 0, and x to the 0, negative 1 to the 0 power is 1, and x to the 0 power is 1. So 1 times 1 is 1. And then it's alternating, but negative 1 to the first power makes it negative, and then I have x squared. So when we put in 2, we have a positive, x to the 4th, and so forth. Minus x to the 6th plus x to the 8th plus dot, dot, dot. So you can see that this is geometric. Geometric, and it converges our radius, our our ratio is negative x squared. So we know that this converges when the absolute value of negative x squared is less than 1. So the absolute value of negative x squared is less than 1. So if we solve this inequality, this tells me x equals plus and minus 1 are my roots. So x equals 1 and x equals minus 1. And if I put in 0, it makes it true. And if I put in 2 to this x squared plus 1, then it's false. And if I put in negative 2, it's false. So my interval is negative 1 to 1. Now the endpoints are not included because then it would be equal to 1 and not less than 1. So this is our interval of convergence. We could have found the radius of convergence using the ratio test like we did in the last section, but our interval was easy to see because we have a geometric series here, and the directions simply said to find the interval of convergence. So we found the interval of convergence accordingly. The next problem says, find the power series representation for 1 over x plus 2. So let's rewrite it to be 1 over x plus 2. And then let's switch it so we have 2 plus x. Let's make a note over here that my 1 over 1 minus x equals the sum of x to the n from n equals 0 to infinity. So this is my pattern that I'm trying to recreate. So now I've got 2 plus x. I need that to be a 1, so let's factor out the 2. So if we factor out the 2, we have 1 plus x over 2, so 1/2 x. If we distribute it, it goes back to that. Let me work through that one more time. If you divide this term by 2, you get 1. If you divide this term by 2, you get x over 2. So here we have that. Now, let's rewrite it to be 1/2 times 1 over 1 plus x over 2. Now I need it to be a subtraction, so let's keep our 1/2 separate. And I have 1 minus parentheses negative x over 2. Do you see how we're fitting into that format now? So now we can say the sum from n equals 0 to infinity. We have 1/2 times, and this becomes negative x over 2 to the nth power because I'm in that power series format. And that's what we needed, a power series representation. Now the 1/2 is a constant, so we could pull it out or we can leave it in. Let's leave it for now because I have a 2 on the bottom and they might work together. So I have 1 over 2, and then I have negative 1 to the n, x to the n, 2 to the n. So let's simplify this matter. On the top we have negative 1 to the n and x to the n, and on the bottom we have 2 to the n plus 1. Now this is called a power series because I have a variable called x raised to a power. So we do have a power series representation. This was our first goal, power series representation. Now, whenever you're dealing with the power series, we want to look at convergence and divergence. And if we go back just a little bit to this term here, we can see that the series is geometric. So this is a geometric series where r equals negative x over 2. So I have convergent when the absolute value of negative x over 2 is less than 1, then I have convergent. So let's multiply by 2, and we have the absolute value of x because the negative gets absorbed by the absolute value of negative turns positive. So the absolute value of x is less than 2. So then we can say negative 2 is less than x, which is less than 2. So our interval of convergence is negative 2 to 2. All right, let's look at another one. it says find the power series representation of x to the third over x plus 2. And that's the way you may see the problem, so that's the way why I wrote it the way I did. Now, off to the side, you need to make a note. I'm looking for 1 over 1 minus x. Now, this x to the third is interesting. So let's pull it off to the side and say x to the third times. We have 1 over, switch those to be 2 plus x. So it's going to be very similar to the last one. X to the third times 1 over 2 parentheses 1 plus x over 2. So let's pull that 1/2 out and call it x to the third over 2. X to the third over 2 times 1 over 1 plus x over 2. So we have x to the third over 2 times 1 over 1 minus negative x over 2. So we have x to the third over 2 times the series of negative x over 2 to the nth power. So we have that power series look. So let's bring this inside the power series. So we have the power series n equals 0 to infinity. X to the third over 2 times, here I have negative 1 to the n, x to the n, 2 to the n. So this means we have the series from n equals 0 to infinity of negative 1 to the n, x to the n plus 3, because we're multiplying the x's on the top, so we add the exponents. And in the denominator, we have 2 to the n plus 1. This x to the third over 2 can move inside like we did down here, because it's x, it doesn't depend upon what n is, so it doesn't matter if it's inside or outside the notation, just in case you're wondering about what happened there. Let's look at a few of these terms. So if we use 0, we have a positive x to the third over 2 to the 0 plus 1 is 1, so it's just 2. So then we have minus x to the 1 plus 3 is 4 over 2 to the 1 plus 1 is 2, so that makes 4. And then we have a plus x to the 3 plus 3 is, x to the 2 plus 3 is 5. And on the bottom, 2 plus 1 is 3, so 2 to the third is 8. Minus x to the 6th over 16 plus. Now we can go back up to this area and see that we have a geometric series. So we know that r equals negative x over 2. So we know that the absolute value of negative x over 2 is less than 1. So the absolute value of x is less than 2. So negative 2 to 2 is our interval of convergence, just like before. This is our interval of convergence. Let's go back down to the series. Now that we have our interval of convergence, let's go back down to here. And this series can also be written as a series. We have a negative 1, we have a 2, and we have an x. Let's call this x to the n. And then we can start n at 3 and go to infinity. Now, if we start n at 3, that means for negative 1 to start off as positive, then we can put n minus 1 or n plus 1. When we put n minus 1, we just need it to start off positive as it did before. And then we need 2 to the first power, so here we need n minus 1 as well. And when you get it into this format, it's easy to see your geometric sequence there as well, because you have n negative 1 to the n minus 1 over 2 to the n minus 1. Let's look at another example. It says f of x equals x squared over x to the fourth plus 16. And it says find a power series representation for the function and determine the interval of convergence. So we're going to start this one like we did before. Let's say that we have x squared times 1 over x to the fourth plus 16. Oh, let's switch those to be 16 plus x to the fourth, so it follows the same format. So we're going to factor out a 16. And then we can add the negative instead of the positive down there. So we have 1 over 1 plus, or that's a minus, 1 minus negative x to the fourth over 16. So this equals x squared over 16 times the sum from n equals 0 to infinity of negative x to the fourth over 16 to the nth power. So then we can bring the fraction that's out front here, this x squared over 16, inside the summation, because it has nothing to do with n. It's a constant, so to speak, in the matter. So we have n equals 0 to infinity, and we have negative 1. Let's do that again. We have x squared over 16 times negative 1 to the n, x to the n, x to the 4n over 16 to the n. So this gives us the sum from n equals 0 to infinity, and we have negative 1 to the n, x to the 4n plus 2 over 16 to the n plus 1. Well, 16 is the power of 2. So we have negative 1 to the n, x to the 4n plus 2 over 16 is 2 to the fourth, n plus 1. So then we have the sum from n equals 0 to infinity, negative 1 to the n, x to the 4n plus 2, and 2 to the 4n plus 4. So do you see how these both have 4n plus a power? And then if we go back, if we go back a slide, we ended up with the negative 1 and the 2 have matching powers, but they're both in terms of n instead of, if you look at this one, that's what we first ended up with, but your powers are completely different, n plus 3 and n plus 1. So this is your simplified form here, negative 1 to the n, x to the 4n plus 2, 2 to the 4n plus 4. So we can use the ratio test here. And we're going to say the limit as n approaches infinity. And we have the absolute value of negative 1 to the n plus 1 times x to the 4 n plus 1 plus 2 over 2, 4 n plus 1 plus 4 divided by, this is a long one, negative 1 to the n, x to the 4n plus 2 over 2 to the 4n plus 4. So we say the limit as n approaches infinity, and we have negative 1 to the n times negative 1, x to the 4n, and that would be plus 4 plus 2, so let's call it x to the 6th, over 2 to the 4n, plus 4 plus 4 is 2 to the 8th, times, we're going to flip and multiply. We have 2 to the 4n times 2 to the 4th. That's hard to read 4 there. And on the bottom we have negative 1 to the n, x, not 4, x to the 4n, and x to the 2. So a lot of these terms cancel out. So we have the limit as n approaches infinity, and the negative 1 becomes a positive 1 because we're an absolute value. And then we have x to the 6th over x squared, so that gives us x to the 4th in the numerator. And we have 2 to the 4th and 2 to the 8th, and that gives us 2 to the 4th in the denominator. So 2 to the 4th is positive, so what we really have to worry about here is we have the limit as n approaches infinity of the absolute value of x to the 4th over 16. Now we know according to the ratio test this converges if it's less than 1. So we know we have the absolute value of x to the 4th is less than 16. Now this could have also been written, the absolute value of x to the 4th over 16 is less than 1. We could have done that from this line up here. The reason that's helpful, and I'm pointing it out, is let's go back. We know from back here that this is a geometric series and that r equals negative x to the 4th over 16. And we know that this converges if the absolute value of negative x to the 4th over 16 is less than 1. And I lean towards geometric, but some of you are going to use the ratio test. Remember, that's our simplified power series. So let's come down here. Now, if we're going to figure out where we have our interval of convergence, we're going to say x to the 4th equals 16. So x equals plus and minus 2. The 4th root of 16 is 2. Then we need to look at our polynomial. Probably it's in between them because it's the interval of convergence, but let's double check that. We plug these values in. Absolute value of x to the 4th is less than 16. This means that 16 is less than x to the 4th, which is negative 16 is less than x to the 4th, which is less than 16. So let's pick a number down here, negative 5. Negative 5 to the 4th is a positive 625, so that's too large. 5 to the 4th is positive 625, that's too large. 0 is 0, and that's correct, because the absolute value of 0 to the 4th is less than 16. So that means our interval of convergence is negative 2 to 2. Let's look at this example, and it says f of x equals x minus 1 over x plus 2. So the problem is you have a binomial in your numerator. So let's make the numerator and denominator match. So let's say x plus 2 minus 3 over x plus 2. Do you see that that's a true statement? 2 minus 3 is still negative 1. So we can split that into x plus 2 over x plus 2 minus 3 over x plus 2. Well, this is the number 1 minus 3 over x plus 2. Now we can look at our power series and say we have 1 minus 3 times 1 over 2 plus x. We're going to switch them. 1 minus 3 times 1 over 2, 1 plus x over 2. So we have the constant 1 out front. We're going to pull out that 1/2. And then we have 1 over 1 minus negative x over 2. And that's our power series set up. So we have 1 minus 3/2 times the series from 0 to infinity. And we have negative x over 2 to the n power. So So we have 1 minus the series from n equals 0 to infinity. And we have 3 halves times, let's do it, let's go our normal way. We have negative 1 to the n, x to the n, 2 to the n. So this means the sum from n equals 0 to infinity negative 1 to the n times 3 x to the n over 2 to the n plus 1. If you may see this cleaned up a little bit, let's put it that way. To look like this, they would put negative 1 to the n, 3 over 2 to the n plus 1, x to the n. Because you have that constant on top, it may tend to look like that. Now, if we go back up here, we can see that our r is negative x over 2. So we can say that this series is convergent when negative x over 2, the absolute value of negative x over 2 is less than 1, is convergent. So the absolute value of negative x, which we don't need to write the negative anymore, is less than 2. So that means our interval is negative 2 to 2. This becomes negative 2 is less than x, which is less than 2. So this is our interval of convergence, even though there's a 1 in the problem. And this is our function back here. Thank you.